Okay, Matt Roscoe here at the University of Montana, a video lecture on transformational geometry, the content area this week for our M595 teaching geometry from a problem-solving perspective. So today I want to talk to you a little bit about, well, what is transformational geometry, return to the definition, and then talk a little bit about, perhaps, leaning towards pedagogy, the opportunities for paper-based exploration of transformational geometry. I want to do one of the explorations I commonly do with my classes of pre-service teachers that perhaps you might consider for developing conceptual awareness of reflection for your students if you happen to teach this topic. Otherwise, it might be interesting to you to see if it helps you develop your conceptual understanding of what a reflection is. Then I want to go on and talk a little bit about, well, what is a transformation, the general definition for this big umbrella term transformation, and then talk about the isometric transformations in grades 5-12, do another paper-based exploration on dilation, and then talk a little bit about the non-isometric transformation in grade 5-12. So let's first talk about, well, what is the umbrella term here, or topic? It's transformational geometry, which is the study of shape, understood according to the size and shape preserving actions of reflection, rotation, and translation, as well as the shape preserving action of dilation. So you can see that transformational geometry really is this idea of actions acting on shapes. And some of these actions preserve both size and shape, and other actions only preserve shape. So let's do a paper-based exploration on one of these ideas, and that is the idea of reflection, which we'll define in a bit. But let's start with the whole perspective. Start from a conceptual standpoint by constructing some reflections and then looking at their properties. So let's fold a piece of paper in half to form two half planes P and Q and a fold line M. Then we're going to open the paper back up and draw three triangles, three vertices in P. Will be one of the triangles. Another triangle will have two vertices in P, 1 and Q. The third triangle will have two vertices in P, 1 and M. The fourth, excuse me, and then number 4, we'll fold the paper back up again and transfer the location of each vertex across the fold line using a push pin. We'll label vertices of pre-image and image, and then we'll connect the corresponding vertices with dotted lines and compare our results with group members is what I usually ask students to do. So maybe I could do this in split screen mode so that you can watch it happen here on both sides. Let's see how this works. No, I think I want to do it that way, but let's hide this so we can see a little better. So I'm supposed to take a piece of paper and fold it in half to form two half planes. I usually tell them to fold it hot dog. I don't think it really matters, but if you're a teacher, you know what I mean by hot dog, I'm sure. So there we go. We have two half planes, P and a Q. And so I guess I'll kind of label those up. Here's P, here's Q. And then, of course, the line itself is the fold line. We're going to call that line M. I mean, it might be worth at least on looking at it from, I guess you can see that pretty well on the screen, but let me go ahead and draw a light line in over the fold line so that we can really see it well. Okay, so there it is. That's the fold line M. And we're going to go ahead now and open the paper back up, draw three triangles, three vertices in P. So three vertices in P would be a triangle that looks like something like that. Okay, and let's label them up. Why not? Let's call it A, B, C. Let's do another two vertices in P, 1 and Q. So let's see. I'll do a vertex here, and a vertex here. Okay, I don't know, let's ABC, how about D, E, F. And then the last one says two vertices in P and one vertex on M. So two vertices on P and one on the fold line itself. So let's put the one on the fold line and do something wild and crazy over here with two other vertices in P. Okay, D, E, F. Let's see, G. How about H and I? Okay, there it is. I'm through bullet 3. Let's try number 4. It says fold the paper again and then transfer the location of each vertex across the fold line using a push pin. So I'm going to transfer it across the fold line. You can kind of see them through there. I don't know if you can see that, but here in my office I can see it pretty well. I can see there's an A right there from my original triangle. I'm going to just transfer it across the fold line using this push pin, which is really just my compass, I guess. And when I transfer it across the fold line, of course, there'll be 3 and of course, I always get the question of, well, how do you want me to transfer that last vertex across the fold line for the one that we actually drew on the fold line? And I say, go ahead and just transfer it. I don't really say anything. I don't try to give it away and do it however you want. Sometimes I see people transferring it like that. Otherwise, they'll open the paper and just punch a hole. And then it says to label the vertices of the pre-image and image. Okay, so pre-image and image. So this was the pre-image, so that must be the image. So that must be B prime. This was the pre-image A, so that must be A prime. Pre-image C, that must be C prime. So that means the triangle that's been transferred across looks like this. I guess I don't really say to connect up. Do I say that? Transfer location, meet vertex, label vertices, connect corresponding vertices. I don't really say draw up the triangle again, but that's what I always tell them in class to do, I guess. So I'll go ahead and connect up these pre-image and image again. Excuse me, not pre-image, the sides. So this was E, so this must be E prime that got transferred over here. This was D, so that must be D prime. This was F, so that must be F prime. This was H, which was on the fold line, so that must be H prime as well, still on the fold line. G got transferred across to G prime here, I to I prime here. And we can connect up the vertices here. The next thing it says is to connect corresponding vertices with a dotted line. So I'm going to connect the corresponding vertices here with a dotted line. Oh, that's too short. I'll get my longer one up. So there's the vertices, corresponding vertices with a dotted line. And you'll get some series of pictures that looks like this. Of course, it's a little bit distracted now with the red lines, but you can see there's a triangle on this side and a triangle on this side, and the lines connecting them, dotted lines connecting them. Triangle on this side straddling the line of reflection, triangle on this side straddling. And then we just have a conversation as a class about the properties that they notice. I mean, first of all, I ask them, well, what does it appear that the construction does? And they all say, well, it's reflecting. It looks like a mirror reflection, often they'll say. And then I ask them, well, how would you define what a reflection is? What is it doing? And you'll hear all kinds of interesting ways that students will define this mathematically. But one of the things that's important is that they start to to notice that, well, it takes a point to a point the same distance away from the line of reflection. Usually they notice distance first. So in other words, what they'll say is, if this is the point here that's on this line in between B and B prime, then this distance and this distance will be the same as one another. This distance and this distance will be the same, and this distance and this distance. And I say, well, it's very easy for you to get the same distance, but that distance, is there anything about direction that we need to know in terms of the line of reflection? And then soon enough, students will say, well, of course there is, that distance is perpendicular in all of these cases, right? So those distances are perpendicularly bisected by the line of reflection. So hopefully they will basically give me the definition of a reflection through I guess the construction, the pen and paper activity. And that's the intent of the activity, is to develop this idea of conceptual awareness of what a reflection does before we actually get down to the more formal and rigid definition of how do we define what it is. I hope that maybe this will give you some ideas about how you might teach reflection in your classes, or think about leading other transformational instruction with some sort of a pen and paper activity before you get into the nitty-gritty of definitions. One other thing I think that's interesting to ask them, other things that happen with reflections. What other properties do you notice? Are any corresponding sides, for example, parallel to one another? So, for example, A prime, B prime do not appear to be parallel at all to one another. But is there something we could say? Well, oftentimes they'll say the angle that it makes with the line of reflection is the same angle over here. So the angles are preserved. So that meaning, the angles in the triangles will probably be preserved. We'll ask questions about how about distances. Is the distance from A to B the same as the distance from A to B? Hopefully they'll notice that indeed these are congruent triangles. So it's an isometric transformation. Distances seem to be preserved, and so do angles. I would ask questions like, well, what would have to be true if, a pre-image and image were parallel in terms of lines? And that's an interesting question for you to ponder. And the other thing that's probably interesting for students to note is that directionality, direction is reversed in reflection. That if we went clockwise from A to B to C in this side in plane P, then in plane Q, where the image resides, we go counterclockwise from A to B to C. So in reflection, the image it reverses its handedness, which is one of the hallmarks of identifying when something has been reflected. I don't know if you've ever noticed this, but when you wave at yourself in the mirror with your right hand, the person in the mirror is actually waving back at you with their left. So there is some argument that we never really get to see what we look like in the mirror because we're seeing a reversed image. We I guess start out with this nice pen and paper activity. I'll scan that and make sure it's available to you on the website. But let's go ahead and get down to it. Transformation, let's talk about this big umbrella term. A transformation of the plane is a one-to-one correspondence from the plane to itself that maps every point in the pre-image to a new point in the image. So any transformation of the plane that preserves distances, that is, it maintains congruency, is called an isometry. So, the article that we read this week, the chapter in the Fostering Geometric Thinking text that we read this week makes a big issue out of this, that, transformation takes every point in the plane to a new point in the plane. And oftentimes it seems like, based on the research, that students think of it as sort of a shape that moves, something that rotates, or a triangle that moves to a new location. And they don't see it as sort of everything in the plane moving according to a certain rule. And so I thought it'd be worth making sure and talking about, the big umbrella term here, which is transformation. This idea that everything in the plane moves according to a rule. And certainly that's the case with with the pen and paper activity we just did, that the idea is that if I have a point in the plane, I pinprick it and it goes someplace new. Um, So what are the isometric transformations? So in grades 512, the ones that are taught there's three of them. The first one is called translation. Unfortunately, that it's so close to transformation, but translation is a transformation of the plane that moves every point in the plane a specified distance in a specified direction along a straight line. So these are often called slides when they're first introduced in 6th, 7th grade. Later on, we give them the name translation. Of course, we're very interested in what happens on the Cartesian plane because later in algebra, we invoke the use of translation um, to talk about the transformation of functions. And so it's important that when we teach this, that we make a connection to the Cartesian plane, that when we translate a point x comma y, what we're really doing is we're adding a value a and a value b to all to that point. And if there are other points x comma y, we always add the same value a and the same value b to those numbers, to those points, I should say. At this point, I want to step out and just talk a little bit about how you can make this really appear or come to life using GeoGebra, and I'll make these GeoGebra files available to you should you find a need for them or want to play around with them. So oftentimes what I'll do is show a picture like this and animate a point and ask students, well, what do you notice about the two triangles? And usually they say, well, I notice that two triangles are congruent. And I say, well, more than that. I mean, if I moved from B to B prime, would it be the same movement from C to C prime, A to A prime? And usually they'll say yes. At this point, what I do is I usually add this little translator and then animate it to try to show them that what's happened is the whole figure has just slid in a certain direction in the Cartesian plane, and in fact every point on the figure is just sliding in the same way as every other point on the figure. So, for example, if I move, let's see. So I think there we go. C to C prime controls the slide vector. So, for example, here. I could think of every point sliding a certain distance down a certain number of units and over a certain number of units. And usually this is enough for students to be able to see why the points are just all going, let's see, down one. Let's make it a little easier on ourselves. So maybe right here. So to get from B to B prime, all we're doing is we're going down. Let's go down one more unit maybe and change B to something a little easier to see. Maybe not. Let's try something horizontal with C. There we go. Now they're all on lattice points is what I'm trying to do. There we go. So if I went from B to B prime, I'd be going down 2 over 2, 4, 6, 8, 9. So it's down 2 over 9. Checking A would be down 2 and over 1, 2, 3, 4, 5, 6, 7, 8, 9. Appears to be true. And then going from C to C prime, I am also going down 2 and over 9. So indeed, what's going on with this particular transformation is that every point in the plane is moved the same distance and direction as every other point in the plane. So the definition seems to be invoked by the actual GeoGebra file. And the last thing I usually do is tell them what the title is, and so I've made that hideable as well. So I'll leave that in the on the website in case you might be interested in using it. Let's talk a little bit about rotation. A rotation is a transformation of the plane determined by holding one point fixed and then rotating the plane about this point by a certain number of degrees, either clockwise or counterclockwise. We call the fixed point a center of rotation, and the angle is called the angle, and we designate counterclockwise rotation to be positive. So we're also very interested in teaching this on the coordinate system. One of the first things we do is talk about 90-degree rotation, and then we extend that to 180 and 270. It turns out that 90-degree rotation takes a point x comma y to a new location, negative yx. 180-degree rotation takes xy to negative x, negative y, and 270 does similar to the 90-degree rotation, takes xy to y, negative x. Of course, those are important, I guess, Cartesian results of rotation. Let's take a look at a GeoGebra file. So let's see, rotation. Here it is. I give students again the opportunity to sort of talk about, what sort of transformation do we have there. The first thing I ask them is, could this be a translation, for example? So we look at, well, from B to B prime, I'm going down 1, 2, 3, 4, 5, and over 1, 2, 3, 4, 5. So that would have to be true for C to C prime. Going down 5 would take me to about, let's see, 1, 2, 3, 4, 5 here, and then over 5 would be 1, 2, 3, 4, 5. So C would have to be about right here in order for this to be a translation. So it's certainly not a translation. The other thing that gives it away is, in a translation, I actually didn't make this point. The sides of the figures pre-image and image, the side lengths or the sides segments that make up the sides are parallel to one another, and certainly that's not the case here. Usually what students will notice is that the figure appears to have been rotated. And I'll ask questions like, well, where do you think the center of rotation is here? In other words, what's the part on the page that hasn't moved? Usually they'll identify some region up here because they sort of see this thing as moving, I guess, down and to the left in an arc. So usually what I do is I put the animation up first, and then let them see that indeed it appears that things are being rotated. And I'll ask a question like, well, what is the center of rotation? Can anybody sort of eyeball it? And usually somebody will come up to the board and put it somewhere like there, or somewhere in the upper right-hand corner, just looking at the movement. And then I'll ask the question of, well, what is the path that a point travels when the plane is being transformed under a rotation? And hopefully what I get back is the paths, which is what P is. Paths are concentric circles centered at the center of dilation. Of course, I can change the center of dilation to be wherever I want it to be because it's a dynamic sketch. I can also change, the shape of the triangle. And I think it's a pretty powerful display of what a rotation is dynamically. Another interesting fact is we can change, let's make this a little bit easier to see on us. I'm going to put the center of dilation a little bit closer to everything. I can put the angle of dilation, excuse me, of rotation, I said dilation. I can put the angle of rotation on the screen and show, well, what happens if we increase the angle of rotation? So this is now being rotated by 135 degree, and you'll notice that it doesn't change the concentric circles at all. All it does is change where the blue triangle, the image, lands. And of course, the closer to 0 I get, the closer it is to the red triangle in terms of the rotation and its effects. The last thing I do is put up a title. So a little bit of a tool there for you to perhaps play around with and pique the interest of your students or yourself. Go ahead and save that and put it on the website. Reflection, which was the one that our pen and paper activity took a look at, is defined actually according to the results of the pen and paper, I guess, paper and pin pricking activity that we conducted. We say that a reflection in a line L is a transformation from plane to the plane that pairs each point P with a new point P prime in such a way that L is the perpendicular bisector of the segment that connects P to P prime. Now that's true as long as there is such a segment, and of course we found out in the activity that there are some that do not have a segment, and that's when P is on L, and if P is on L, then we say that P and P prime are coincident, they're the same point. One of the things we do a lot is explore around with this on a coordinate plane, and you might go and try this and convince yourself that reflection in the x-axis is a function from the plane to the plane, such that the image of the point with coordinates x, y is taken to x comma negative y. If we're reflecting in the y-axis, then we're going from the plane to the plane, such that the image of the point with coordinates x, y is reassigned to negative x comma y. Let's take a look at the reflection activity here. So one thing I love about reflection is that students usually notice that it's the only one of the three isometric transformations that reverses orientation. It seems like if you make the line of reflection vertical, they usually recognize it pretty quickly. So there's the reflected. I tried to make this look kind of like I guess, a page turning in a book. So you can see the triangle is taken across a line of reflection to a new triangle. Here's the line of that corresponding vertices. If you connect corresponding vertices up, there are those lines, and then of course the line of reflection. And the line of reflection is adjustable, so we can take it wherever we want. But anytime we do that, what we notice is that these lines that connect, say, B and B prime up are perpendicularly bisected by the line of reflection. And that's true regardless of where I start. So if I start with, say, an obtuse triangle like this, I can still see that perpendicular bisection relationship. Interesting, and something you should always do is probably put the line of reflection on the segment itself and see what happens when it's right on the segment itself. Then of course it is its own image. So if I moved, for example, C onto D, I would see something like that. So a nice visual display of reflection. I'll go ahead and clean this up and save it and put it on the website for you to play with. And that takes us through, I guess, the last of the isometric transformations. It's worth noting that any movement in the plane on a flat surface can be written as one of these isometric transformation, or a combination of two of them. So it turns out that this is incredibly important in for example, computer programming, where transformations of things like desktops are happening all the time. Really, there were only three tools necessary: translation, reflection, and rotation. Let's try another paper-based exploration. This is the one I usually do to motivate what a dilation is. And let's say what we're going to start with is I have a little worksheet that I'll put on the website, but we're going to draw a 3, 4, 5 right triangle, choose a center of dilation outside of the triangle, and dilate the original triangle by a scale factor of 2, and then repeat with the following centers. So a dilation where the center of dilation is inside, where it's on a vertex, and on a side. This is a fairly small piece of paper, so I think I'll hide this and make this large so we can see it well. Let's see, that's not picking up, is it? Let's see here. There it went. Glad I looked. All right, so we're going to start with a 3, 4, 5 triangle. I'm going to put it, draw it easily by doing 3 vertically, 4 horizontally. And I guess this will be 5 by Pythagoras' theorem. We're going to choose a center of dilation outside of ABC and a scale factor of 2. So I don't know, I guess I'll put a center of dilation. Let's see, we'll label this A, that B, and this C. And there's a couple different ways we can do this. If we're going to dilate, what we're going to do is we're going to take every point, and make it twice as far away from some center of dilation. So this is dilation 1. So if I was to sort of try to figure out what that distance is, I of course could use Pythagoras to find out, using the little right triangle there to find out what its horizontal and vertical components are and square rooting that. But I think it's easier just to say, well, to get from D1 to A, I have to move 3 over and 1, 2, 3, 4, 5 up. So if I just double that, I move 3 over and 1, 2, 3, 4, 5 up, I get to right here, and that's my A prime. I hope that makes sense. What I've done is I've just doubled that distance, right? That distance has been doubled. So every single point in the plane is just being doubled in its distance from D1. Let's do the same thing for B. If we say B, we go over 3 and up 2, and then we would go over 3 more and up 2 more, and that would get me to, let's say, a B prime. And one of the things I notice here is that if I doubled that distance, then these 3 lines or 3 points, I guess, are collinear. They're all on a line. See, to get to C, I go over 1, 2, 3, 4, 5, 6, 7, and up 2. So I'll go over 1, 2, 3, 4, 5, 6, 7, and up 2 more. Did I go up 2? I think I went right there. And I'll draw that in. And I'm going to call that C prime. And I'll go ahead and draw in my triangle, original and dilated triangles. So a little bit heavier handed in terms of what you need to teach kids, in order to do this, but the idea is we're just taking every point and we're doubling its distance from a center. That's a dilation with scale factor 2. And the questions I usually ask kids are, well, what can you say about, triangle ABC? And I'll draw it in a little bit here so that we can see it. The pink triangle, that would be the pre-image, and let's get a green one, the green triangle, which would be the image under the dilation. I usually don't ask those questions until the end, but let's go ahead and try repeat it with D2 inside ABC. So let's try that. 1, 2, 3. 1, 2, 3, 4. So here's ABC. So here's my A, my B, and my C. I don't know, I'm going to pick that as my center of dilation, D2. Okay, let's transform A first. We go over 1 and up 2, so I'll go over 1 and up 2 more to get to A prime. To get to B, I go over 1, down 1, so I'll go over 1 and down 1 further. I need to move where my label is, I guess. So this will be my B prime, A prime. To get to C from the center of dilation, I go down 1 over 1, 2, 3, so I'll go down 1 over 1, 2, 3, and that'll be my C prime. And so I can see okay, so interestingly enough, it looks to be the same size and shape as the green triangle. One thing that I've noticed when I'm doing this is that this side and this side are parallel, and that can be said for all pairs of corresponding sides. The same thing is true here. A prime B prime is parallel to AB. A prime C prime seems to be parallel to AC. B prime C prime parallel to BC. Let's try, we've got D2 done inside. D3 is at a vertex of triangle ABC. Let's try see what that looks like. So let's see, A, B, C. I almost always see them choose the right angle vertex as the center of dilation. I don't know why that is. Maybe it's just some sort of psychology going on. But let's say I choose B as my center of dilation. So this is going to be also D3. So B and D3 are coincident, 2 points on top of one another. So to get to A, I just simply go down 3, so doubling that distance, I would go down 6 from there to get to A prime. To get to C, I go down 3 over 4, so I go down 6 over 8. 1, 2, 3, 4, 5, 6, 7, 8 to get to C prime. And drawing in those sides, I get something that looks like this. And again, I see this parallel nature of sides in their images. AC is parallel to A prime, C prime, BA and BA prime. Oh, and by the way, this is still B prime, right? Because B itself is its own image if it's the center of dilation. A distance 0 doubled is still a distance 0. Okay, last one. D4 is on a side of ABC. And I should say on a side, by that I mean it's on a side, but it's also not one of the vertices. I should probably say that in the instructions. 1, 2, 3, 4. Okay, so I always think this is an interesting one for them to experience. So what if I put the center of dilation, let's say right there, and call this A, B, C, and this is D4. So I go 2 to the left to get to B, so I'll go 4 to the left to get to B prime. I go 2 to the right to get to C, so I'll go 4 to the right to get to C prime. And then to get to A, I go over 2 and up 1, 2, 3, so I'll go over 2, 4 and up 1, 2, 3, 4, 5, 6, and that will be A prime. And I'll get something that looks a lot like this. Again, the things that I hope that students notice when they do this experiment is that they notice that basically the larger triangle is similar to the smaller triangle, the scale factor, of course, being 2. Also that corresponding sides in a dilation are parallel to one another. Corresponding angles are congruent to one another. What other things can we say? Orientation is preserved, so there's no change in left-handedness or right-handedness of the figures, so very different from, for example, a reflection. Lots of the properties about dilation can be inferred from the activity, and let's go ahead and formalize that now. I hope you have a chance to maybe use that in your own teaching at some point or something like that. So we say that a dilation is not an isometric transformation. The reason is that it doesn't preserve length. It does preserve shape, though. The definition, the strict definition, is that a dilation with center D and a scale factor R strictly greater than 0 is a transformation from the plane to the plane that pairs each point A with a point A prime in such a way that DA and A prime are collinear. They lie along a line, and the distance from D to A prime is R times the distance from D to A. So all we're doing is we're expanding everything by a factor R from a center at D. One of the things we usually discover, or students discover, is that under dilation, the image and pre-image are similar. That is, corresponding angles are congruent, but the sides are not congruent, but are all in a common proportion. So in the case of the investigation that we did with the pen and paper, the corresponding sides are in a common proportion 2 to 1. Also interesting, under dilation, the image of a segment is parallel to the pre-image of the segment. That is, if A prime, B prime, C prime is a dilation of ABC, then we can say that AB will be parallel to A prime, B prime, AC parallel to A prime, C prime, and BC parallel to B prime, C prime. Okay, that is really all I had for today or this week on transformation. Just a romp through the 5-8 rigid and non-rigid transformations, or isometric and non-isometric transformations. In your content exercises for this week, what you'll be doing is investigating images that have been transformed and trying to decide which are which. So it's sort of a sleuthing activity. Please let me know if you have questions about that, and I look forward to your submissions. Have a nice week.